Swayam Prabha. Digital India. Educated India.
That was an excellent question. This filtering operation that I'm talking about is with LES in mind. That's what I was doing, and so it's a great question. So what would happen in RANs? I want to tell you that it's not that different. So what happens in RANs? Certainly, I want to use this picture, and I don't have the RANs picture, but I just want to talk it through. In RANs, you have this black line, right? This black curve, which is what the actual data is. This black curve, I said that is with all the details, all turbulent, where the particles are. But we do an ensemble average. So in other words, this is, I'm taking, the way to think of this, I'm taking a horizontal cut section, say from one end of the bucket to the other end of the bucket. I've taken the velocity at one realization. And I repeat this experiment again. Now, that will be another slightly different black curve where there may be particles somewhere else. And you collect 1,000, 10,000 black lines, and now you average it. That's what you're doing in ensemble averaging. That's how you derive a RANS model. The greatest advantage is that you don't have to tell what big L is. You don't, unlike in LES, there is no filter. You're doing ensemble averaging. Now, in this case, ensemble average, which has nothing to do with a length scale, may be like this. Let me pick a different color. An ensemble average. That is the average quantity, average over all the realizations. It's an ensemble average. And this purple line is what we decide to compute. Now, the good news is that sometimes this, if it's a steady flow, the purple line is just has no time dependence. But the green line or the red line or the blue line, they will be changing over time. It's an LES simulation. So in LES simulation, you can do different LES simulations depending upon the filter that you choose. But in RANs, it is ensemble average. So your grid must be sufficient to resolve the purple line. Okay? But the averaging in the next line, in the next few slides, I said, okay, take the Navier-Stokes equation and you do the filtering. Instead of filtering, every time I use the word filtering, you can replace it by ensemble average. And you get the same thing. Okay? So in other words, lots of models that we need to do for LES, you will have to do in RANs as well. Okay? So RANs, you don't need to choose a priori a filter width. That's an advantage. Your problem may be one dimensional or may become time independent, etc. So those are certainly great advantages. And of course, when you do ensemble average, it doesn't make a whole lot of sense to do Lagrangian simulation. I don't know, does anyone do RANS simulations with Lagrangian particles? It makes much more sense to do Euler-Euler RANS simulation. So it makes the problem much simpler. But the downside is that every model that we are going to talk about, in LES, we only have to model subgrid portion. So in other words, if you were to choose a finite, a very fine filter width and choose the red curve, okay, what you need to model is far less. If you then decide to do, okay, I am going to do a broader filter, then the blue line may require more modeling because more turbulence is being modeled. If you choose green, much broader, you have to model even more. In RANs, you have to model every bit of the turbulence, okay, and therefore the models are much more sensitive. The other thing you may all know in LES is that if the filter width is in inertial range, then it is easier because inertial turbulence is easy to model, and therefore you may get universal models with LES, but in RANs you may have to fine tune your modeling. So there are advantages and disadvantages. Now going back to your question, one of the advantages in RANs model is that it's the purple line is the answer. So you got to choose the grid and you can refine the grid and try to get that RANs answer. Okay. But in LES, if you refine the grid, your answer changes from the red line to the blue lines to the green line. So grid independent study is very hard, in fact impossible with LES, is that the answer changes as you change the grid. So the classical CFD concept of grid independent study is really very difficult. Okay. So that is another thing that you might want to think about. Okay.
So
Yeah.
to ask that, is it difficult or does it not make sense?
It does not make sense, you are right. So it can be difficult, but in the sense that you see there are two ways to do LES. One, you apply filter explicitly and you do the simulation, but that is not how, when you think about it, all the theory I talk about triple integral filtering. When you use the Euler-Lagrange LES scheme, nobody does that. You just start with some equation, right? So in other words, therefore what happens is when you do that, when you put a fine grid, you are solving a different problem. You are solving for the green line or the blue line or the red line depending upon your grid. Therefore, how can you expect your answer to be the same? But in RANs, it is only the purple line, and you can say I am going to put more and more grid and I am going to get purple line, much more sensible. In LES, you are shooting a moving target. Therefore, every time you resolve the grid finer, you want a better answer. So it will never be stable. So that in that sense, you are right that even the classical make your grid half in every direction and you compute, and if your answer is the same, then your grid converged. Here it is not quite that way. Okay. But what I said is difficult because if you do a very fine grid, then you have to apply a coarse filtering on top of it, then you can compare a coarse grid calculation. So it can be done, but it is hard. Okay.
So follow-up question with regards to filter size. So we have to keep in mind the particle size as well, because if the filter size is somewhat comparable to the particle size, then our averaging models won't work, right? For Euler, I'll jump to Euler.
Yeah. Yeah, you are right. Your averaging volume is better if it is bigger than the particle, because otherwise what happens is, think of this, if your filter size is of the order of your particle, your grid will be so big that your particle is so big in it, right? And you are not resolving the flow. So you have a point particle which is as big as your grid size. It starts making less and less sense, and you are going to use a drag law which is good only on an average sense. Like yesterday we talked at length about it. Who are you averaging over? Now, on the other hand, if your filter width is bigger than the particle and your grid, so in particle resolved simulation, you want at least 20 or 30 grid per particle. In Euler-Lagrange, you want your grid so that you have 20 or 30 particles inside. It does not make any sense to do Euler-Lagrange simulation so big. But in your case, you have been tough luck, because if you have shock, okay, to resolve the shock you must have small grid, but on the other hand particles may be big. So, compressible flows are very hard problems, okay. But other fluidized bed, etc., one would need to choose, if you are doing Euler-Lagrange or Euler-Euler, you should choose a grid which is fairly not of the particle size, maybe at least 5 times 10 times bigger than, so that you will have good number of particles inside your cells, so that when you use average drag and it makes sense, etc. Okay. Okay. Yeah.
Can you please explain in short about the ensemble averaging in transport?
What do you mean by that?
Sir, so while explaining, you have used the ensemble averaging that is going on with that blue line, right? That was average.
So, what I am saying is that you have this black line, right. So, there are no red, blue or green curve in an ensemble averaging. Okay. You have reality, which is the flow. So, you are saying in Rand's model, you are saying I am not interested in computing this black flow, but I want only to compute the average flow. So, what is that an average flow? So, this blue is what the velocity will be along one line in one realization. You do another realization, you will get, since it is chaotic turbulent problem, you will have statistically similar looking, but there will be holes wherever that particles are, etc. So, you build hundreds of these black lines, they all are slightly different, and then you say I am going to average that. Just like I said, where the particle is erased, when you do LES, you do not have to worry, am I inside the particle, outside the particle, etc. That equation is good everywhere. Same thing applies for RANS. That is why in RANS you do not have to know where the particles are, etc. You just average it. And that I just drew it as a purple line. So, in other words, there is, if you have a fluidized bed and you do an ensemble average, you may have some big eddies, etc. Now, your job is to compute, the RANS model is trying to compute that smooth flow, which has no turbulence, it is a smooth flow. Okay. That only depends on large scale variations or ensemble average variation. So, you have a much easier job of actually numerically simulating. So, you have transferred all the computational difficulty to modeling difficulty, right. So, RANS model is easy to compute, but will it give good answer? Well, it depends on your models. When you do particle result simulation, it is hard to compute, but your answer you can trust. And LES is somewhere in between. I did not say this, maybe this is good time. So, basically if you filter the indicator function, you will get volume fraction, because we are averaging. Indicator function just counts whether you are inside or outside particle. So, when you later in the next slide, in the next lecture, I am going to show average mass balance equation, etc. There you will get terms like volume fraction, average velocity, and so on and so forth. Okay. So, let me stop there and I will show you what the outcome of averaging. Okay. So, let us talk about mass balance. Okay. So, you take the Navier-Stokes the incompressibility equation. Okay, I wrote it in the compressible form. You could just take divergence of the velocity and I multiply. This is the standard approach. I say that, well, I am going to take this only where the fluid is, and I am going to fuzz it out. I am going to filter it, and whatever comes out is the mass balance of the filtered field. And this is where averaging and time derivative, averaging inside I have spatial gradient. So, I got to take the derivatives outside and bring the integrals inside. When I do that, I use Gauss rule, Leibniz rule, the details are there. Okay? And you do this and you get this equation, because you can see the bar is inside the derivative now, time derivative. So, in other words, I have swapped the integral filtering operation and the derivative operation. Okay? And the same thing here, I have divergence of an average. And this averaging, I said Favre averaging, is the average of the density times velocity. So, this is what is called Favre average velocity. This is the average density. Well, if the fluid is a constant incompressible flow, then this term is 0, and I will talk about it in a minute. So, but the important thing is that it comes out of Gauss rule and Leibniz rule, is that you account for the mass exchange between the particles and the surrounding fluid. Naturally comes out of this operation. So, finally, what you get is this is the filtered mass balance equation. It looks like compressible mass balance equation. So, what we and by the way, this quantity, while here rho f and u etc., the raw quantities, fine scale quantities are defined only outside the particles. After filtering, this volume fraction, density, velocity, u c tilde, all these quantities don't care. They are defined everywhere over the entire domain. And that is why we don't solve it outside particles or anything. We solve it everywhere. Okay. And this equation looks like standard equation. So, there is no our goal is always to get equations that look like standard equations, so that you can push it into Fluent or whatever, any code that you can simulate. Okay, so that all the CFD techniques of a single phase can be used for multi-phase as well. Okay, and that is why we want to write this in this form. And mass balance, this filtering doesn't cost anything, no damage, no models to be done, except you have to model this. What is this term? It is the mass released by the particles into the fluid. I mean, that makes sense, because right now I am saying mass balance equation for the fluid, and there are a bunch of particles in there, and if they are evaporating, it is a mass source. Now, it needs to be modeled. In a particle resolved simulation, you will have flow around it, you can calculate what the evaporation rate, lots of things are condensation rates, everything you can precisely calculate. Now, all you know is that there are a bunch of particles inside, and you got to come up with a model what the evaporation rate of these droplets or condensation rate in case of rain formation, etc. Okay? So, in other words, this is one modeling that needs to be done, which is nothing but every time you will find that what we need to model is how the fluid is talking to the particles. Every physics you must model, because we just averages everything. So, we have to talk about, you need a drag model, you need an evaporation model, you have a burn rate model, you need to have a heat transfer model, everything must now we have to come up with. Okay. So, here is the first model, which is the mass source model. Now, of course, if there is no evaporation, this goes to 0, and then it greatly simplifies the problem if there is no mass exchange between the particles and the surrounding. But many of you are doing bioreactors and things like that. Unfortunately, this mass exchange is important often. Okay. So, that is all I have for mass balance. Any questions on that? So, this is just we do exactly the same thing for momentum. We do the same thing. Compressible Navier-Stokes equation, only only where there is fluid, filtered, you integrate. So, you are basically taking Navier-Stokes equation and we are sort of moving around and fuzzing things out. And then we are asking what comes out, I want to write it again as a Navier-Stokes like equation, so that I can use the same technique. And let's see, what do I have? Because I don't want to go through the details, there is a lot of detail. So, one of the things that happens is that Reynolds stress, I mean many of you have taken courses in Reynolds stress. So, what happens is that linear terms like this have no problem, but when you take this term and you will get a term like this, when you after you bring the integral inside the derivative, you get divergence of average of rho u u. Now, you only have average of rho and average of u, but you don't have a average of rho u u. So, this is where you get the Reynolds stress term, for example. So, you approximate this, this is what you get after averaging, but this is what I really want to have, because this looks like Navier-Stokes term. So, in other words, this is what you have, this is what will make it look like Navier-Stokes equation. The two are different because there is subgrid stress. Okay. So, in other words, if you systematically do for every term and say, hey, I want a Navier-Stokes like, I want to make this term Navier-Stokes like, I want to have this term Navier-Stokes like, then there will be extra terms like subgrid stress, subgrid something else will appear, and finally you get this equation, this, okay, very rigorously derived. So, you have, this looks like compressible Navier-Stokes equation. The only difference is that the phi c volume fraction comes in, because if you take a unit volume, you are, remember, this is the penalty of saying I am not going to worry about inside particles or outside particles. I said that we are now looking at the fluid velocity average. So, the fact that the particle is only occupying phi c of the region, you have to have that phi c. This phi c is the one, this volume fraction of the continuous phase is the only place where you know that only that much fluid is there. Okay. So, now you have, this is written in compressible form, you can write in the incompressible form version. So, this looks like time derivative term, this is the advection term, and this is the gravity term, this is the viscosity term. So, this is written in this way. So, one, this term, this term, this term, this term are just the standard one. This guy, this guy, this guy you better model. You have to model. What are these terms? So, this guy is subgrid stress, that u bar term that I was talking about. This is what Reynolds stress term that you have in any Reynolds averaging model. There is nothing new, but now written for compressive, I mean the multi-phase flow. Okay. So, this is the effect of subgrid turbulence. The only thing I will say is that now this turbulence may not be only classical turbulence, but it may include pseudo turbulence. Okay. It's okay. So, in other words, it is turbulence that is not resolved, that is smaller than your grid, is the same as a single phase problem, but the turbulence, so it's basically Reynolds stress or LES subgrid closure, but you may want to think in terms of the turbulence that you close is maybe different because there is some pseudo turbulence in there. So, in other words, you got to model this term tau SG, you have to model it, but that modeling you may just simply use whatever people use for Smogirinsky closure or dynamic Smogirinsky closure or whatever you can use. Okay. But keep in mind that you are doing it for a multi-phase turbulence. Now, these two terms are what's how the particles are talking to the fluid. You remember in the mass balance you have a little m dot, which takes care of what's the mass exchange between particles and the fluid. Now, remember, when there is mass going from particle to fluid, it carries with it momentum, it carries with it some energy, etc. So, mass exchange gives rise to this momentum exchange between the particles. Now, this is a direct momentum exchange, which is what the drag. So, in other words, force exerted by the fluid on the particles, the reverse of it will be applied back on the fluid. So, these are coupling terms, how particles and the fluid are coupled. Since you have fussed out all the details, now you have to model them. Okay. So, at the momentum stage, there are three important things that you have to model. Now, let me say one more little thing that you have to model. This is stress, divergence of stress, and stress is related to viscosity times strain, right. Now, remember we talked about maybe a couple of days ago that viscosity of a multi-phase flow will be different. Therefore, this term is also, you can't quite put whatever you do for us without particles, you may have to model and change it. So, modeling happens in this term, in this term, in this term. This term, of course, if there is no mass exchange, you can set it 0. But this usually is important, this is the drag. This will be the slip effect, the fact that the particles and the fluid are not moving together. If the viscosity of the mixture is substantially different, you got to use that in writing stress in terms of strain.
Okay. So, a question regarding that. When we are using the phi c, which is the volume fraction.
Yeah, volume fraction of the fluid. Yeah.
Fraction of the fluid,
which is 1 minus volume fraction of the solid.
So then viscosity, why can't we consider only of the fluid phase?
That's what you remember, we talked about it. Okay. If you take a rheometer and you move this, you do an experiment only with fluid, with particles. To push it, pull it at velocity u, you have to apply more force with particles. What would you say that? Viscosity has increased, effective viscosity has increased. So, when there are particles, effective viscosity changes, and that's what we derived as a Einstein's viscosity correction. Yeah. And same thing happens, instead of pulling the plate, low temperature, high temperature, just fluid, fluid with particles, conductivity changes, heat transfer increases, okay, or can decrease, depending.
Based on the model that we are using, Euler Lagrangian or Euler, so both would require this correction.
Absolutely, yeah, yeah. But usually, so now you can ask, so remember we talked about multi-phase flow effects, volume effect, inertia effect, buoyancy effect, slip effect, thermodynamic and transport effect, they are all here. This viscosity change will be thermodynamic and transport effect. If you have a high speed flow like a rocket, you will just happily throw this term, because its gravity effect is negligible, because it is going at high speed. Whereas someone doing a sedimentation problem, this is the main thing. Now, this is often very important because this is the drag term, that is the slip effect. Now, if the particles occupy only 1% of the volume, I will remove this, I will remove this, I will remove this, because it is almost 1 everywhere. Volume effect is small. Those are the things that I was talking about. When I said that this equation, people never use it the way I write. They will do all sorts of stuff. They will say, oh, this is not there, that is not there, I throw this out, I keep this. They are all very smart people and they make very good choices. But as a student, when we are sitting there and we look at it, we say, oh, this equation is very different from this, why? Now, you see, this is like a master equation. Try to keep everything in it. I certainly do not want you to simulate this. You want to start with this and say, I don't think this is important for me, so I am going to drop this. And I am going to, this is really, really important, I am going to keep it. That's what the decision that you have to make. Yeah. Okay. With that, I'm going to stop. So we now have filtered the equation. Okay, and now you know what do you get when you rigorously take Navier-Stokes equation. In this case, I took compressible Navier-Stokes equation and you filter it. This is what you get. Okay. Any questions? I think everybody is interested in lunch, so they don't ask questions. Thank you.